Okay, so I'm pretty excited about today. He's leaving. So obviously we're talking about Mulliken molecular symmetry, and we talked about the point groups, right? Finding the point groups and finding the character tables and so on. And today we're going to be discussing the character table in general, like what the rows mean. Yes, thank you. And then let's make this laptop. Come on, show screen. Okay, good. And so we're really going to focus today on the character table itself. And so that's why I passed out all the character tables. You can look at those and compare them, all the different character tables. And then we'll discuss those rows, the Mulliken notation rows. And we're going to discuss all of the motions that a molecule can make: rotation, translation, and vibration. So you see the character tables there in front of you. You can see them here on the screen. And these allow us to determine, today we're going to look at the symmetries of the molecular motions. And then on Friday, we're going to expand that to the molecular orbitals, because we can use the character table to learn about both of those things. Now, when we were determining the selection rules earlier, I showed you how symmetry can help us with the selection rules, and how we end up having these different functions, their symmetries multiplied by each other, and that the end result was that if we have an integral over all space of a wave function times an operator like light times another wave function, because we've got two wave functions involved, and then we have light that's causing the transition, whether it be directly or through Raman scattering. We still have two wave functions, and we have some light operator in the middle. And so we have the integral of those three functions multiplied by each other. If we just know the symmetries of those things, we can simplify that and determine whether that transition is allowed or not. Because if all of this multiplied by this, and this ends up with an even function in the end, then we know the integral will be non-zero. Now, in these character tables, we have lots of rows, and those rows are going to represent everything in the molecule. So if there is an asymmetric stretch, it will be a particular row in the character table. If there's a symmetric stretch, it'll be a different row in the character table. And when we are evaluating the symmetries of these in terms of even or odd, only the top row is even. Now, I can't say that AG is even or A1 is even, because that depends on a particular point group. I can say that the top row, no matter what it is even. So look at your character tables and look at the top rows of all of the character tables. Sometimes it's A prime. See up there the CS? It's A prime. In CI, it's AG. In C2V, it's A1, right? So I can't say it's a particular A1 or AG. I have to use a more general term. I have to say top row. So in all of these, the top row is even, and all of the other rows are odd. So after we do these direct products of our wave functions, our light operators, and our other wave functions, if we don't have a result that contains the top row, sometimes it's a sum of several symmetries. If one of those is not the top row, then the integral is equal to 0, and the transition is forbidden. Make sense? Okay. Because again, this definition, the integral of an even function is non-zero, the integral of an odd function is 0. And then we use those multiplication rules. So let's dive into this character table of water. So this that's surrounded in blue is actually the character table. These things over on the right-hand side are just extra bits of information that are helpful to have. There's a character table for every Schoenflies notation, or for every point group. And you can look at the character tables that you have in front of you. Notice when you determine the point group of the molecule, now you know the character table. So it's incredibly important to get the structure right and to go through the flow chart or have a knowledge of how to determine the point group. Because if you get the point group wrong, then you have the wrong map, and you're using the wrong map, and you're going to get to the wrong destination if you have the wrong map. Okay. Now, So you'll hear me use the word Schoenflies notation. So this is what that is. That Schoenflies notation is the point group designation. And you'll hear me say Mulliken representations or Mulliken notation, and that's the rows of the character table. So these are vocabulary words that you need to know. The Schoenflies notation is that point group. The Mulliken notation is the row of the character table. Make sense? It's just you have to memorize these things because there's no reason. Who knows Mulliken? Who knows Schoenflies? You have to just associate those things with the correct pieces. And these ones in the middle, those are the characters. So when we talk about a character table, those are the characters that we're talking about. And they represent what happens when you do a C2 or a reflection or an inversion. And then these over here, these are Cartesian and rotational basis functions. So it's helpful to know the symmetries in this character table of the x-axis, the y-axis, the z-axis. It's helpful to know like the dz squared or dxy. You can put your atomic orbitals in here using those xy, xz, and so on. You can put the vibrations and molecular orbitals in here and using analogies to these axes in Cartesian basis functions. And then again, this top row is even, and so any integral over all space that has A1 in it will be non-zero, even if it's a sum. So if you end up after several direct products, ending up with a sum here, as long as the integrand contains A1. It contains A1, therefore it's non-zero. And you can think about this as an integral. If it's an integral of a sum of functions, then you can take that integration of each part of that sum. And the one that is the A1 part, that's the non-zero part. The integral of the B2 part is going to be zero. Okay. Now, odd symmetry, if you end up with any of these inside the integrand, and remember those angled brackets mean where it's an integral over all space using Dirac notation. Integral over all space of an A2 function of B1, those are going to be zero because they're not top row. Okay. So that's the character table. We're going to dive in now to this idea of irreducible and reducible representations. So the character table is a compilation of all of those. We call them vector representations of the point groups. The vector is that row of ones and zeros and so on, those characters. And there are two types. There's a reducible and the irreducible. The irreducible representations are what you have in the character tables. Now, a reducible representation is what we're going to start with today. So we're going to do a reducible representation of all of the motions in the molecule, and then we're going to break it down into its irreducible representations. It's called decomposition. So we're going to take this reducible representation, and then we're going to decompose it. Right? It's composed of something, and we're going to decompose it. We're going to pull out all of the parts and see which rows are inside that reducible representation.
So it's kind of like taking a number and factoring it so you get tall triangle.
Yeah, it's kind of like factorization. Yeah, and there's particular equations that are given to you to do that. Now, let's talk about the Mulliken notations. The letters do mean something. They have some rules associated with them. So one-dimensional rows have A or B labels, and determining between A and B is under rotation. So it's an A if the rotational character is a +1, and it's a B if the character under rotation is a -1. So you can see that over here on the C2V character table. You see the C2 rotation. The A's here are +1 under C2, and the B's are -1 under C2. Now I talk about one-dimensional rows. The dimension you can find under the E designation. So right here, this tells you the dimension of that row. So if we come down here to this one under the D3D character table, or let's do C3V, it's simpler. Under C3V, you see under E, we have a 2 here. And that means it's a two-dimensional row. And unfortunately, the two-dimensional rows are labeled E. And the identity operator is labeled E. I'm sorry. I didn't do this. It's not my fault, okay? So in the same table, you have two things labeled E, okay? So context is important. The column label is the identity operator. So up here, these are symmetry operations. Okay, these are Mulliken notations. So there's an E that's a Mulliken notation, is the labeling scheme right here. So if you ask me what is E, I'm going to say it depends, right? Is it a column heading or is it a row? Or are you talking about energy? Right? So this isn't energy either. I'm sorry. There's just no way to get around it. This is, and I don't want to come up with my own labels because then it won't match any book anywhere, so I have to teach you what's in the books. So we just have to deal with it. Context is important.
You haven't convinced them to change it yet.
Yeah, they're going to be like, well, you can't change this. This is, immovable. There are some three-dimensional rows. Again, you can see a 3 under the identity operator. Go to tetrahedral, if you will. Find tetrahedral character table. You see it? Yeah. What's on that row? So scoot over to the far right. You see in parentheses, you see X, Y, and Z, don't you? On that T row. Okay. That's showing you that the X coordinate, the Y coordinate, and the Z coordinate are degenerate, right? They have the same energy in that symmetric molecule. So that molecule is almost spherical. So in a spherical system, X, Y, and Z would have the same energy. Just think about that as the px, py, and pz orbitals. They have X, Y, and Z symmetry, and in a spherical system, they have the same energy. Px, Py, and Pz. Look, octahedral. Is octahedral nearby? It also has T's, and it has that X, Y, and Z on the same row. If you're doing an MO diagram and you're wondering where to put label the Px, Py, Pz orbitals, you would go, if it's an octahedral system, you'd go to the character table and you would label those Px, Py, and Pz with that Mulliken notation. What is it? Who, those of you that are looking at it, what row is that?
T1U.
T1U. So T1U is the label that you would use for the p orbitals in an octahedral system. Okay. And so you can see where those labels, you've learned that, right? In the d orbital splitting, you can see a T1U splitting, and then what is the other one? What is the E? Is it E2U? EU, yeah. So you see that kind of splitting in those d orbitals. Okay, then subscripts. If you have an inversion center, and not all molecules have that, obviously, but D3D here has an inversion center, and you have negatives down here and positives up here, and that's what gives you the G's and U's. See? So under D3D, you see G's and U's. If you see G's and U's, that tells you there's an inversion center. So look at the tetrahedral character table. Very symmetric molecule, but it does not have an inversion center, so there are no G's and U's. Okay. And then G is just German for gerade, or gerade is German for even, and ungerade, or uneven, is odd. So, now let's talk about our reducible representation. This is a reducible representation, and I'll teach you how to get this, but I'm just giving it to you right here. These characters are the characters of the reducible representation that contains all of the motions of the molecule. And how do we get that? Well, we use this equation here. So this is a way to go through all of the operations, the symmetry operators in our character table, and to determine what the character under each one of those operators would be for all of the motions in the molecule. Y'all are searching. Is it not in the notes? Is it? Did you find it? Okay, you have it. Okay, just making sure. And so let's unpack this equation here, because it's got a lot of new variables for you. Okay, this character here, this chi, Greek character chi, represents character underneath the symmetry operator. And so this right here is what we're calculating right here. Okay? This NR is the number of atoms unmoved by the symmetry operation. So if we're going to do E, okay, then this is the number of atoms in my molecule that are unmoved. And we'll see the molecule in a second. It's water. It'll pop up here in a second. In terms of this plus or minus 1, how do we decide which to use plus or to use minus? It depends on the operator that we're using. So if we're using E or C2, okay, we use a plus. And if we're using I or reflection, we use a minus or an SN. Okay. If we're using any of those, if we're in any one of those columns, then we use that minus sign. And then we have a K and an N. For identity or reflection or inversion, N and K are all both equal to 1. And so we just put a 1 there. If it's rotation, then we know what the N is. Like a C2, N equals 2. If it's like a C2 minus 1, then K is minus 1. So you could have a plus 1 up here or a minus 1. Sometimes the character tables will have a minus 1 up there. It's just rotating in the other direction. And so that would be K. This is equal to K in the terms of that rotation. And so now let's look at examples for water. Okay, so let's do this reflection in the YZ plane. So here we have water. And you see all of the little coordinates are put on all the atoms. So we have X, Y, and Z for this hydrogen, X, Y, and Z for the oxygen, X, Y, and Z for the hydrogen. And if we reflect in the YZ plane, okay, that's the plane of the paper. And essentially the X-axis has gone to the other side. You see that? So I'm just trying to show reflection. The molecule's unmoved. And we know that water would be unmoved by this operation because it has this symmetry element. It's in the character table for water. So all the atoms are going to look the same. But essentially, if we reflect in the YZ plane, this X-axis reflects to the other side. And you see that here. Okay? So I'm just showing you reflection. Let's use this equation now. So the number of atoms unmoved, we have the hydrogens and the oxygens, they haven't moved with this reflection. Okay? So that's the 3. Does everybody understand where the 3 comes from? Okay. Then we're using a minus 1 because we're doing a reflection. Okay, that's using this rule right here. Use a minus 1 for reflection. Okay. And then for reflection, N is equal to K, which is equal to 1. So we have a 1 here and a 1 here. And now we can evaluate this expression. So we have the cosine of 2 pi, which is 1. Okay, it starts at 2 pi, it goes down, it starts at 1 at 0, goes down to minus 1 at pi, comes back up to positive 1 at 2 pi. So cosine evaluated at 2 pi is equal to 1. We're multiplying that by 2, so I have 2. Okay, and then we're adding in a negative 1, so we have 2 minus 1, so we have plus 1 here. So this whole parenthesis adds up to plus 1 times 3, so we end up with 3. And so then that is the number that goes right here. You see how we're doing this? We use this equation to come up with all 4 of those numbers. All right, let's do the next one. Let's do XZ reflection. So now we're reflecting it in the XZ plane. You see the XZ plane? It goes through the center mass of the molecule. And so these hydrogens move. So they're not counted. So how many unmoved atoms do we have? We just have 1. The oxygen is sitting in that plane, so we only have 1 unmoved oxygen. So it's only 1, and that's oxygen. I put oxygen, oxy, okay. So if I just put a 0, you think it's 0. Okay, then for reflection, K is equal to N, and we use a minus. So reflection, we use the minus sign, and a 1 and a 1. And so we end up with this Same piece in here. This whole thing adds up to 1. And then that's multiplied by 1, so we end up with 1 here. So that's where we got that character. Okay. Let's do E next. So we do the identity operator. By definition, the atoms don't move. And so we have 3 atoms unmoved. We're using a +1 because it's E. We have a 1 and a 1 because it's E. And so now we can evaluate this. This is 1 times 2 gives us 2, plus 1 gives us 3. So 3 times 3 is 9. So that's where that character came from. So you just work your way through this equation, and it's telling you, I know you don't believe it yet, but it's telling you all of the motions of the molecule. Okay? And then this last one, the C2 rotation. So it's a rotation, so we use a plus. It's a C2, so n equals 2 for a C2. So now we've got the cosine of pi, not the cosine of 2 pi, and that's -1. -1 times 2 is going to be a -2. -2 plus 1 is a -1. -1 times 1 is -1. Okay, so that's where this -1 came from. So we're done. And that is what we call a reducible representation. It is not an irreducible representation. So this reducible representation is the sum of other rows in a character table. And so now we'll decompose it to see what those rows are and how many of each there are. But we can't start that unless you're comfortable with this. You just work your way through this equation using the definitions or the rules given here in gray. So you follow these rules here, and you get the reducible representation. We'll do another one for ammonia if there's time. Okay. Looks like everybody's following me so far. All right, so now let's reduce this. So here's our character table. I've put the reducible representation across the bottom. Now, we've got a lot of new definitions here. We have 4 symmetry operations, so 4 columns. We call those classes. So there's 4 classes. It's a different K than we had before. Okay, so this is a totally new K, so context-wise, the number of classes is also labeled K. By coincidence, I'm sorry. Yeah, I didn't do that. The numbers in front of each of those classes would be kind of like a degeneracy number. It's GI is the number of members in each class. If you look at the C3V character table, there's some numbers in there that are other than 1, right? You have a 2 in front of the C3V and a 3 in front of the sigma. Do you see the C3V character table? It should be on the front page. C3V, you see that?
Yeah.
So, and sometimes the number of classes is not 1. In that case, there'd be 2 C3s and 3 sigma planes. Follow it? Okay. Now, if you add up all of those, they add up to the order of the group. And so for ammonia, the order of the group would be 6. For this molecule, for water, it's 4. So we add up those 4 columns. Actually, we're adding up all of the coefficients of each of those operators, and that equals 4. And then the number of irreducible representations equals the classes. And so the columns and the rows are going to be equal, meaning the tables are square. So if you'll notice that in all of the character tables, the number of columns and the number of rows are equal. Okay, the columns are the number of classes, and you have the same number of irreducible representations. So now let's decompose this reducible representation. What I mean by reducible is this right here is the sum of the irreducible representations with some coefficients in front. Like I might have 3 A1s and 1 A2 and a couple of B1s. And that will add up to this total, this 9, -1, 1, and 3 vector. So we're trying to figure out how many A1s we have, how many A2s we have in this total set of the vibrations and rotations of the molecule. And so this is the equation that we use. And I've color-coded it because it's really confusing with all of these new variables, okay? So this right here, this A of mu, that is this little guy here. That's the coefficient. That's the number of a particular type of Mulliken notation or particular symmetry. And it's equal to this equation. We have this red number up here, the number of members in that class. We have the blue number, which is our character of our reducible representation. And we have the green number, which is the character for A1 in this particular case. So let's do this. We'll learn by example. So we'll do one. So that equation is now written down here. I have the coefficient for A1, and that's equal to 1 over 4. Where did 4 come from? That is the order of the group, this 4. Okay. So this is G, right? And then it's the sum of 4 terms. And I have the GI number here in red. I have the reducible representation character in blue. And then I have, because I'm dealing with an A1, you see that right there, that A1? I just pull the character from A1. That's all I'm interested in right now. And I put it there. And that's the first term in my sum. Since I have 4 columns, I'm going to have 4 terms in my sum. Then the second one is the C2 character. So this guy right there. The -1 from my reducible representation. And then the row for A1, because I'm working on the A1 row. You see how all of these numbers come from? So here the 3, is from that 3. The 1 and the 1 are from the red and the green ones. So you just build this up. And this is really nice because when you get to the end of this sum, you have 9 here. So I have 9. This becomes a -1. This becomes a +1. This becomes a +3. Okay. So I have 9 minus 1 is 8. +1 back up to 9. +3 more, 10, 11, 12. So the sum is 12. And it's divisible by 4, which gives me 3. So that tells me there are 3 A1s in this reducible representation. See what we're trying to do? We're taking the reducible representation. We're trying to see how many A1s we have. We have 3 A1s. It's not that bad. It's just a weird equation, but if you know how to use this equation, it'll pull out the number of A1s you have. Then we do the same thing, but for A2. So now we're using a different row. We're using the A2 row. So instead of the green numbers, we're pulling down the orange numbers. Everything else is exactly the same. Only we're just pulling down the orange numbers instead of the green ones. And so let's go ahead and add it up. We have a 9 here. We have a -1 there. We have a -1 here. We have a -3 there. Okay. So 9, 8, 7, 6, 5, 4. So we end up with 4 divided by 4. We end up with 1. Now this is nice because if you've done a mistake and it's not divisible by 4, you know you have a mistake. Exactly. Yes. Yeah, that's right. Fractions don't exist. You can't have half a row. Okay. And that is, I caught, even building these slides, I caught an error. I didn't pull the 3 down or whatever. I didn't pull the -1 down, And so I ended up, instead of the -3, it was a +3. So it was 9, 8, 7, +3 is 10. And I'm dividing by 4. And I was like, I got a problem. Yeah. And so that's really nice. It's forgiving. If it's not divisible by the order of the group, then you know you've made a mistake. Okay. And so now we know we have 1 A2 in this representation. Let's do the B1s. So now I'm pulling down the purple row. So everything else is the same. I'm just pulling down a different row. So I'm using, because I'm doing B1s, so here's B1. And so I'm pulling the B1 numbers down. So I have 9. Okay, I've got 2 -1s. They cancel, so I have a +1, a +1, and a -3. So 9, I have 10, 11, then 10, 9, 8. So I end up with 8 divided by 4 is 2. So I know I have 2 B1s. And so again, this is telling me that in all the motions of the molecule, 2 of those motions are B1. and then we'll do the last one here, B2. So here I'm pulling down just the last row numbers right there. And so let's go ahead and do the evaluation. I have 9 plus 1, because the two negatives cancel, minus 1 plus 3. So 9, 10, back down to 9, then 10, 11, 12. Divided by 4 gives me 3. So I know I have 3 motions that are B2. So now let's think about our motions. And so we have this, now we've reduced it into the number and types of irreducible representations here. And let's look at our translations. If the molecule is moving in X, Y, or Z, that's a motion. And we can go to the character table, and we can see where X, Y, and Z are. We see that translation in Z has the symmetry of A1. So one of these motions is the Z translation. And one of these motions is the B1 translation, and one of these motions is the B2 translation. So this takes up one of these right here. And this takes up one of each of those. So the B1, one of those is the X translation. The B2, one of those is the Y translation. Now the rotations. Look in the character table for C2V. You see RZ is on the A2 row. So this single one right here is the RZ. That single A2 that we have in all of the motions of the molecule, that happens to be the rotation around the Z-axis. One of those B1s is the rotation around the Y, and one of those B2s is the rotation around the X. So if we take out the translations and the rotations, what do we have left? Yeah, so we now know we've checked off one of the A1s as translational motion. We have 2 remaining ones that are vibrational. So this tells me in all of my vibrations, 2 of those vibrations will be A1 symmetry. Isn't that cool? So at least it kind of narrows it down. What are the possibilities for my vibrations? 2 of them will be A1. I've used up both of my B1s here. And so I've got 0 B1s and I've got 0 A2s in my vibrations. But I've only used up 2 of my B2s, and so I've got 1 left, and so I'll have 1 vibration that's a B2. So that's pretty handy. It helps me determine what are the types of vibration symmetries that I could have. And so here's all of the motions in water. The translations, the X, Y, and Z translations come from that table, that Z, X, and Y. And so we see that A1 is the Z. We see that the X was the B1 here, and the Y was the B2. We have the 3 rotations for a nonlinear molecule, and that's the rows that we have here. You know, we have the A2 and the B1 and the B2 for those. And so then we have the 3n minus 6 motions that are left. There's only 3 left, and those have to be A1. 2 of them have to be A1, and 1 of them has to be B2. Now, we have these arrows, which we could figure out if we understand the character table, which ones are A1 and which ones are B2. But I'm going to leave those arrows for next time, because we're actually going to generate these pictures. So we're going to use the projection operator and the character table on Friday to generate these arrow pictures. So where these arrow pictures come from, they actually, on Friday, we'll see where they come from. At this point, we're just looking at the types of symmetries we might have the types of symmetries we will have for our vibrations. Okay. And that's it. So we're not done. We're going to do ammonia next, but that's the full analysis of water. Okay. So you can make that the reducible representation for all of the motions in the molecule, then decompose it into the number and types of symmetries that we have, and then you can go through and analyze the translations, X, Y, and Z, or the rotations, RX, RY, and Z, and whatever's left are the number and types of symmetries that you have for your vibrations. And that's what this course is about, the symmetry and spectroscopy. So if we're going to do spectroscopy on our vibrations, understanding the symmetry of those vibrations is helpful. Okay. Let me pause, though, for anything that you need clarification on.
So on this particular slide, I understand why it's asymmetric stretch. I think I can see why they're considered symmetric stretches in bends, but I can't put into words. So how would you explain why those are symmetric?
The word symmetric or asymmetric is somewhat conventional. Okay. When we're looking at a molecule like this that has two identical bonds, the OH bonds, when they both expand together, that's what we mean by symmetric. So the symmetric stretch is all of the bonds that are identical are elongating at the same time. Make sense? So it's doing this. So both bonds are elongating at the same time, and they're identical bonds. So they would call that the symmetric stretch, and this would be the asymmetric stretch. So one bond is elongating while the other one's shrinking, and so we call that asymmetric. So the word in the cases of describing stretches, symmetric and asymmetric, is not exactly tied to top row. Okay, so that's why that's a sort of a deeper question than I think you intended. So by symmetric and describing stretches, we because the symmetric stretch may not be top row. Okay, it could be a symmetric stretch of the methyl group where all three CHs are expanding at the same time. You know, and it may be top row, it may not be, but we call that the symmetric stretch because three identical bonds are extending at the same time. Okay, and the asymmetric stretch would be the others. Look at that, I can. Okay, so anyway, I practice. All right, so we're going to do the ammonia next because it has a different character table and different numbers of classes and so on. So there's my ammonia molecule up at the top, three identical NH bonds. If you go through the flow chart, you see that it's a C3V molecule. So the Schoenflies notation is C3V. And let's fill out this reducible representation for all of the motions in the ammonia molecule. And so here's our equation with the same sort of definitions. So let's do E first. So we do E on the molecule. Now we have 4 atoms unmoved. We're using a plus because it's E. Okay, the 1 and 1 also because it's E. Okay, so this is 1 times 2 is 2. Plus 1 is 3. 3 times 4 is 12. So we end up with 12 up here. So the reducible character under E is 12. Okay, then we do a C3. This one's kind of interesting, okay? So we have a plus here because it's a C. We have a C3 because it's a C3, right? That 3 goes there. Now I had to look this up. I had to calculate what is the cosine of 2/3 pi, okay? It's nice. It's a 0.5, okay? So negative 0.5 when we multiply by 2 is a minus 1, okay? Minus 1 plus 1, we get 0. And so the character, or reducible representation character under C3 is 0. Okay, yeah. And that's okay. Because it's a combination of pluses and minuses, and they might equal out and cancel it out to 0. And then we'll do the sigma V. So there's 3 of those. We're not really figuring out, notice we're not caring about which sigma V. We're doing all 3 at the same time, essentially. So this, we have, but for any one of the sigma V's, let's just do the plane of the paper up here. So we're doing the plane of the board. We've got these atoms are unmoved. So since 2 atoms are in the plane of the reflection, they're unmoved. So everybody understand why that's a 2? Yeah. We didn't talk about the rotation for the C3. The nitrogen was unmoved, right? And here the NH in the plane of the reflection is unmoved. So it's a 2. We use a minus 1 here because of the sigma. We have a 1 and 1 here because of the sigma. So we have the cosine of 2 pi, which is 1. 1 times 2 is 2. 2 times minus 1 is minus 2. Oh, no. 2 minus 1 is a plus 1. Okay, and so I screwed up. So yeah, 2 minus 1 is 1, and then 2 times 1 is 2. So then the reducible character under the reflection column is 2. So that's going to contain all of the representations of all of the motions of ammonia. Let's decompose it. So now we have some different members in each class. We have 2 C3s, and you can think about that molecule. We could rotate it clockwise 1/3 of a turn or counterclockwise 1/3 of a turn, and we would move those hydrogens to different places. So they are unique operations. So if I put a little star on this hydrogen, if I rotate it this way, it'll end up over here. If I rotate it the other way, it'll end up over here. So those are unique rotations because they put the labels in unique places. Okay. So we have 2 C3s, and the same thing with the reflections. I have 3 unique reflections. So those are the members in each class. If I add up all of those members, I get 6. So now in our decomposition equation, we're going to be dividing by 6. So if our sum is not a multiple of 6, then we've done something wrong. So we're going to decompose this into the particular rows using this equation. So we have 1/6, and then we have, again, the red number, the blue number, and the green number. So we have 12 here. We have a 0 here. So the blue number, all of these middle terms are always going to be 0, no matter what row we're adding in. And so this is going to be 0. And then we have 3 times 2, okay, which is 6. So 12 plus 6 is 18. Divided by 6, we get 3. All right, so that's great. So our first number is 3. We have 3 A1s in the motions of this molecule. We can do the next one. We have, again, 12. We're using the orange row, 0. And now we have a -6. We have 3 times 2 times -1, so -6. So 12 minus 6 is equal to 6. Divided by 6 equals 1. So we have 1 A2 in this molecule. And then the last one, we're pulling down the purple numbers, 12, 0, and 6. No. What's that?
The first one would be 24, 12 times 2.
Yeah, there you go. I knew I made a mistake. 12 times 2. Yeah.
30.
Yeah, 30. So, wait a second. Oh, no, this is a 0. See? It's harder than it looks. 0. Okay, 24 divided by 6 is 4. Yeah. Yeah. Okay, very good. This is embarrassing to do on YouTube. Yeah. And so then we have 4 E's. So 4 of these motions are E. Yes?
And for some, if you look at what you just E, but you saw the operation as A2. Or is it A1, A2, A2?
What did I do?
Far left.
Far left.
Far left. Oh, yeah, just a copy-paste error. Thank you. So let me change this down here. Whoo, stop. Okay. So I need to scribble this out and make it E. Yeah, that was a copy-paste error. Thank you for catching that, because that would be confusing. So props. Okay, so then we have 3, 1, and 4 as our numbers and types of the different symmetries. So now let's look at our character table and see which one of those is translations, which ones are rotations, and all the remaining ones are vibrations. So we have 12 total degrees of freedom. 3 of these motions are translations. And so one of those A1s is a Z translation. Now, this X and Y are in parentheses. That means they count as 1E. Okay, so that takes away 1 of the E's, not 2. Okay, because E's are 2-dimensional, so they have 2 pieces to them. So translation in X and Y count for a single E. Okay, and so we subtract those 3 translations, and then we have rotations. Again, RZ is the A2 one, so this one is right there, the rotation around Z, and then RX and RY, we subtract those 3 rotations, so we should have 6 vibrations in this molecule. Water had 3, we add another atom, we get 3 more vibrations, so we have 6 vibrations, and this is what's left. We have 2 A1s left over, And it looks like if you count each one of those as an E, that we would have 0 E left over. But because they're in parentheses, that counts as a single E. This is in parentheses, so that counts as an E. And so we have 2 E's left over in our vibrations. Okay? And so this counts for 2 vibrations, and each E is going to be 2 each, and so this is 4 vibrations. 4 actual motions, and the symmetries, they're coupled in pairs, and so that's going to be our 6 vibrations, because the E's count double. Okay. So that's what we would have for ammonia. So now I know I've got 4 symmetries, 2 A1s and 2 E's, to label 6 vibrations. Now, the symmetric stretches are the easiest to identify. So in this case, if I stretch all 3 of these bonds the same direction, okay, that is going to set up an oscillating dipole that grows along the z-axis. And so if it has Z symmetry, it's going to be on the A1 row. So one of those A1s is the symmetric stretch. So in this case, the symmetric stretch happens to be top row. So that's coincidental. So we have that symmetric stretch of the NH bonds, and that's going to be the top row. That's going to be one of those A1s. Let's think about the umbrella motion. If I have these angles, if I have 3 angles, theta 1, theta 2, and theta 3 back here on the back, right? What's the molecule gonna do if I decrease all 3 of those angles?
So you get them closer to the planar?
Decrease or increase.
Okay.
If I increase them all, it'll become more planar.
Yeah.
If I decrease them all, it'll shrink. They'll get closer together. And so you could look at this also as a symmetric bend, because all 3 angles are going in the same direction. If all 3 angles are shrinking and expanding together, then that's a symmetric bending motion. We call it the umbrella motion because it looks like you're inflating an umbrella or opening an umbrella. And so that symmetric bend moves the hydrogens up and down, which is also along the z-axis, which is also going to be A1. So the symmetric stretch in ammonia and the symmetric bend in ammonia are both A1. So that takes care of both A1s. All the others are going to be E. So ammonia is pretty easy to analyze. The symmetric stretch and the symmetric bend are both A1, and then any other deformation, like if I extend one bond while shrinking the other 2, then that's going to be an asymmetric stretch, and that's going to be E. And if I have another kind of arrangement of the asymmetric stretch, it'll be E. And if I increase one bond angle by decreasing the other 2, then that's going to be an asymmetric bend. And what we call a deformation, that's going to be E as well. We'll get into how we get those angles and bond arrow stretches and so on next time when we use the projection operator. So today was focused on the rows of the character table and the motions of the molecule and how to build a reducible representation and decompose that into the irreducible representations that individually represent all the motions in the molecule. All right.